So last time we recognized that this solution, this kind of object which is the solution to the Klein-Gordon equation, we showed it to satisfy a simple harmonic oscillator equation. So we wrote this where the weights for the momentum are here in the phi function, and the phi function obeys the simple harmonic oscillator equation. So phi plus c squared p squared plus m squared c to the fourth over h bar squared. Maybe we should write this with all these constants is equal to 1, but let's carry them along for now because we wrote them before. So this equation, again, obeys, this is the same as a simple harmonic oscillator equation, where this is the position of the oscillator. And so we know how to solve this. So we have a formalism to solve this. So you remember the Hamiltonian is p squared over 2 twice the mass plus 1/2 m omega squared x squared. But in this case, it would be this thing squared, the phi squared. And we showed how we could write the x in terms of ladder operators. So we had something like 1 over... There are different ways in which we can derive this, but we can define it like this with the frequency and have so it's a sum of the different ladder operators, right? What is this one called? This is the one that creates the state, the one that eliminates the state. The A plus and A minuses, right? A and A plus, A cross. And then we had the momentum, which has some complex thing. I think it's minus I. We have the frequency, something like that. And then it's a difference of these two operators. And the condition that position and momentum don't commute, in other words, the uncertainty principle, right? We remember that to come out as that when we operate on a wave function. Therefore, this translates into something on these ladder operators. So we're not going to rederive all this, but this is done in the quantum class. Equals h bar, I think, but let's make h bar equal to 1. So if that's the case, I think it ends up looking like that. And then we notice that the Hamiltonian ends up being written, if we bring the h bar in again, it's h bar omega. We have the energy. And it's going to be combinations of A plus and A, or A cross and A. This was one way of writing it, and there's another way of writing it where we switch these two, if you recall. And we found that basically the state N is created from the ground state, 0, let's call that 0, with these operators A cross n times. So we have to operate on this n times. We get that kind of a thing. And the spectrum of energy, right? So recall the energy spectrum, we ended up showing that it's n plus 1/2 times h bar omega, where omega is the frequency of the oscillator. And so let's get another sheet here. So we're going to take this formalism and carry it over into this program. And so what we have is that the phi, sorry, we call this psi. So the psi of R and T, we call this psi of R and T, this ends up being an integral, d3p over 2 pi cubed. We had, where's our, all right, we're going to replace this phi of p and t with these ladder operators. And so this is going to end up giving us a combination of a e to the I p r plus a cross the cross is minus I p r. Sorry, I actually wrote this as I'm writing. I write this. I'm forgetting about time for the moment. Let's just look at psi of r. So it'll look like that. It's a combination of these kinds of objects, but this then brings in these ladder operators, and so we really should distinguish here. These have they should have an additional label here for different frequency or different values of p, the momentum, and so that's the sort of the wave function looks like that, and then we have the normally it's called pi, but this is sort of the momentum. Which is, so let's see, we're trying to think of this kind of an object. So we wrote this kind of an object, right? So we put this into the superposition, and now let's think of this kind of an object. And so that gives us the 2 pi cubed. We have a minus I. We have some constants, frequency for different p's. So maybe we should put p's here, times this AP, e to the I p r. We have a minus sign, a cross, and p, e to the minus I PR. These are the position and momentum quantities that we now end up with. So what we realize is that we were thinking of this as a description of one particle, and in fact now we recognize that really this is a collection. This has to be a collection of many particles, or of many simple harmonic oscillators, and basically this collection of particles is what we call a field. So what we have is that the free particle is really a field. We're having to deal with a field of simple harmonic oscillators. That's what special relativity and quantum physics together sort of seem to generate. And so we could start with a field kind of quantity, start from a different perspective, get a Lagrangian for the harmonic oscillator, for a field of harmonic oscillators that are sort of all together, and end up at the same place. And so maybe we'll approach this from that different perspective as well.